Hey everyone, and welcome. Today we're going to jump into a proper chemistry showdown. Haloalkanes versus Haloarenes. These guys are like two sides of the same coin, but they behave so differently. So let's get right into it and figure out what's going on. So here's the big puzzle for today. On one hand, you've got this super reactive molecule, and on the other, its cousin, which is just incredibly stable. They're part of the same family, but one's a live wire, and the other's totally chill. So what gives? What makes them so different?
And you know what? The answer to this whole thing, it's all laid out right here in these amazing toppers notes. Seriously, all the secrets are inside. So let's decode them together, shall we? Let's jump in.
Okay, so let's set the stage. Think of this as a tale of two cousins. Our main characters, the haloalkanes and the haloarenes, both have this one thing in common, a carbon-halogen bond. But that's pretty much where the family resemblance ends. See, with haloalkanes, that carbon is just part of a regular chain, aliphatic. But with haloarenes, it's part of that special, super stable aromatic ring. And that one single difference, well, it changes everything. It gives them completely different personalities.
All right, first up, let's meet the reckless cousin, the haloalkane. Now, before we get into why this guy is so ready to cause a ruckus, we've got to ask, where does it even come from? How is this little troublemaker born?
So there are a few standard playbooks for making them. You can cook them up from alcohols, alkanes, or even alkenes. And then there's this cool trick called halogen exchange. You might have heard of the famous Schwarz and Finkelstein reactions. That's what those are. Basically, a bunch of different roads, all leading to our one, very reactive molecule.
Okay, check this out. Let's zoom in on one of these methods. The Lucas test. It's a classic. When you're starting with an alcohol, you add this Lucas reagent, and you just watch. How fast does the mixture get cloudy? That cloudiness, or turbidity, tells you everything. If it happens instantly, boom, you got a tertiary alcohol. Takes a few minutes, secondary. If nothing really happens, well, you're looking at a primary alcohol. It's such a simple, clever test, and it's all about how stable the thing that forms in the middle of the reaction is.
All right, so we've made our haloalkane. Now let's talk about its personality. And its main trait is, it's always looking for a fight. It's super reactive. Its go-to move is to just kick out that halogen atom and swap it for something new. That's its whole game.
And this favorite game of theirs, it has a name, nucleophilic substitution. Basically, a nucleophile, something that loves positive charges, comes along and says, out of my way, to the halogen. Simple, right? Well, not quite. Here's the twist. There isn't just one way to do it. The haloalkane actually has two different paths it can take, SN1 or SN2.
So what's the deal with these two paths? Well, SN1 is like a two-step dance. It's a bit slower. First, the halogen leaves, forming a carbocation intermediate, and then the new group comes in. This works best on crowded, tertiary carbons because those carbocations are more stable, and it loves polar protic solvents. On the other hand, SN2 is like a ninja attack, one single swift move. The new group attacks as the old one is leaving, all at once. It needs a clear path, so it hates crowded molecules and loves primary carbons. And for this, you want a polar aprotic solvent. Two totally different strategies.
And you can see this perfectly right here in the notes. Look at this example on the left. It's a crowded tertiary one. See how it goes through that two-step SN1 mechanism? But now look at the one on the right. It's a primary haloalkane, nice and open. It goes for that super fast one-step SN2 attack. It's amazing, right? The molecule's own shape decides its fate.
Okay, enough about our hyperactive friend. Let's switch gears and meet the other cousin, the haloarene. And this one is the total opposite. Think of it as the calm, stable, wise elder of the family. It doesn't just jump into reactions for no reason. And this brings us right back to our big question. Remember how the haloalkane loved nucleophilic substitution? Well, the haloarene couldn't care less. It just ignores it. So why? What is the secret to its incredible stability? Why is it so chill?
And the answer is right here. The notes break it down into four key reasons, the four fundas of its stability. You've got the partial double bond character, the instability of the phenylcation, a different kind of carbon hybridization, and finally, some electron-electron repulsion. These four things are the secret sauce to its zen-like calm.
Let's zoom in on the big one, the main reason, resonance. See those lone pair electrons on the halogen? They're not just sitting there. They actually get pulled into the benzene ring and start dancing around with the ring's electrons.
This sharing, this delocalization, creates what's called a partial double bond between the carbon and the halogen. And let me tell you, a partial double bond is way stronger and shorter than a regular single bond. It's like putting a lock on it. A nucleophile just can't break it easily.
So does that mean the haloarene is just a couch potato, a sleeping giant that never does anything? Well, not exactly. You can wake it up, but you have to really, really push it. Or you can get it to play a completely different kind of game, one that it actually enjoys.
And when I say push it, I mean you gotta bring out the heavy machinery. Take a look at Dow's process, for example. To get chlorobenzene to do a substitution, you need insane conditions. We're talking 623 Kelvin and 300 atmospheres of pressure. That's not just persuasion, that's like putting the molecule in a pressure cooker. It really shows you just how tough that bond is to break.
So okay, if it hates nucleophiles, which are rich in electrons, what does it like? Exactly the opposite. It likes electrophiles, things that are electron poor. Why? Because that whole benzene ring is a big, beautiful cloud of electron density. It's a perfect target for an electrophile. And this is the game haloarenes prefer to play. It's called electrophilic substitution reaction, or ESR.
And a perfect example of this game is right here in the notes, Friedel-Crafts oscillation. You can see it right there. Instead of trying to break that super strong CX bond, the electrophile goes for the ring itself. It just swaps places with one of the hydrogens. This is the haloarene playing on its home turf, completely in its element.
All right, so we've met the whole family. The wild child haloalkane and the super stable haloarene. We've seen where they come from and how they act, so now it's time to lay it all out. The final word in this chemical family drama. And here's the final scorecard. It really all comes down to this. Your haloalkane, it's got a simple, breakable single bond, so its whole life is about nucleophilic substitution. It's highly reactive. The haloarene, it's got that strong partial double bond thanks to resonance, so it prefers electrophilic substitution, attacking the ring, and is way, way less reactive under normal conditions. It's that simple. Two cousins living two totally different chemical lives. You know, this whole story is more than just about these two molecules. It's a perfect illustration of one of the biggest rules in all of chemistry. Structure defines function. A tiny little change in how something is built can completely change its personality, its entire destiny. It really makes you think, doesn't it? What other massive family feuds in the world of chemistry are decided by something as small as the character of a single bond?